Welcome, everyone. Hopefully you can hear me. Looks like it's working. All right. Okay, so hopefully I'm sharing these slides a little differently this time. I'm sharing PowerPoint and then doing a slideshow. So hopefully you can see it when I maximize or when I do the slideshow view. Were you able to see that? Is that coming through okay? Great. Excellent. Okay, so go back to here. Slideshow that. Oh, actually, I'm going to start at interfacing. Here we go. Okay, so last time I started covering the material on interfacing, and I started out with this diagram or design of the internal structure of an embedded chip, an embedded system on chip. So an embedded chips these days are comprised of many different modules internally, and generally they're controlled by a CPU, one or more CPU cores, but then they have all these other peripherals that are integrated directly into the chip. And the reason it's done that way is because it's cheaper to try to pool most of the hardware needed for an embedded system, to pull it all onto one chip. So the little gray rectangle is showing the chip, is the boundaries of the chip basically, and then the little rectangles inside there are submodules, and then the arrows that are pointing outside the boundaries of the gray box are I/O pins. So those are the connections to the outside world, and so the CPU is basically isolated inside that chip, and it communicates with the outside world through interfaces, which are peripherals. Hold on, I heard a chat message. Good question. How is this course different from an embedded systems course? That's a good question. So originally, this was going to be more of a hands-on course where we'd actually build things. Although I can tell you that the embedded systems course in our department is designed more for performance-oriented programming, where we build a system on chip, sort of like the one I have shown here, but we build on an FPGA, and an FPGA is a reprogrammable chip. And then we write code in C to interact with the peripherals on there. And generally speaking, the way I ran it, at least, I don't teach it anymore, but the way I taught it, we wrote graphics code and then used different methods, both in hardware and in software, to speed it up, to increase the number of frames per second. Whereas this course is more focused on interfacing and control. At least that's the idea now. Of course, most of these concepts are now kind of conceptual. But originally the idea was, we're going to get a bag of parts and you guys were going to build something with them, solder wires together and test them and then write some code. But now we're basically, this is, some departments might even refer to this as an interfacing course. When I was in grad school at the University of Pittsburgh, we had a course on, yeah, I agree. When I was in grad school, we had a course on, it was called interfacing, and it was kind of similar to this course in a way. The students, had components and wrote code to have them communicate. But then again, I mean, so to give you a little bit of background, I don't want to take too much time, but when I first started teaching embedded systems in our department, I don't know, 10, 15 years ago, I did a survey. I looked at how other universities taught embedded systems, and I found that it was wildly varying. In some universities, some departments, like at Carnegie Mellon, which is one of the bigger computer science, computer engineering programs. They actually had 6 different embedded systems courses, believe it or not. They had one that focused just on kind of control theory, and then they had one that was all real-time low-power systems. They had one that was designed for robotics, specifically for doing control of robotics, because they have a, they're big into robotics there. And then I forget what the other ones were, but they had different sort of flavors of embedded systems. Embedded systems is a really broad topic area. You could focus on different aspects of it. So as I mentioned in my other course, kind of answer your question, my other course was more about tuning software for embedded systems and doing some hardware software co-design, whereas this course is really more about integration. And we're focusing on low power embedded Internet of Things and cyber physical systems. So I'm going to introduce, as I mentioned last lecture, I'm going to talk about control theory. Obviously we have a whole course on control theory in electrical engineering, but none of you guys will take it most likely. So I'm going to cover a little bit of control theory. Obviously, it's not going to be as thorough as if you took a whole course on it. And then I'm going to cover real-time systems as well, real-time scheduling. And again, you could teach a whole course on that. But I'm going to touch on, various topics that are related to cyber physical systems. And so another way to say it is that this is kind of a lower end course. So originally the idea was to use 8-bit processors in this class, whereas in embedded systems we use 32-bit processors that are embedded on the FPGA. So they're in other words, this is a course on lightweight chips, whereas 313 or our embedded systems is on heavier weight chips. Of course, not as heavyweight as like a server processor, but still heavier weight in the sense that they're more capable. Not necessarily battery powered, right? Okay, sorry, that was I'm sorry for being way too long-winded. I tend to be that way. Okay, so back to interfacing. So, and by the way, for the record, I also this slide actually came from my embedded systems course originally, my 313 course. I've modified it and I've spruced it up, but this is originally one of the first things we talk about in embedded systems too. So let's see, let's go back here and slideshow. And of course, I hit the wrong key. Okay, so this is a system on chip. The point of this is that the CPU communicates with peripherals through load and store instructions through special memory addresses. That's the main way that the CPU initiates communication with peripherals. The peripherals, the communication is handled through I/O registers, sometimes called status and control registers, but that term is a little kind of out of date at this point. But an I/O register is just a memory address and a description of an address or range of addresses and how to use them to communicate with peripherals. This is not generalizable. Every one of the I/O register maps and I/O register descriptions and the way you use them is specific to each peripheral. So in order to figure out how to use the I/O registers of a particular peripheral, you have to look up its data sheet or its documentation. So one of the questions I might ask you about this is, what is the size of the I/O space associated with one of the peripherals here, which is the USB, and this is basically just a subtraction problem. It would be the upper range of the addresses minus the lower range plus 1, because it's an inclusive difference. So, and of course you have to deal with hex. So you have to. I'm assuming you guys are comfortable. I'm hoping you guys are comfortable with hexadecimal representation and arithmetic here. So in this case, the USB peripheral has a 256-byte address space, and of course these peripherals will have their own, they'll have different I/O registers, different numbers of I/O registers, different address ranges. Some of them will be, have a fairly wide address space, whereas some of them may just have 1 or 2 registers, depending on the complexity of the individual peripheral. As I mentioned, this is a key point in bare metal programming, because this is something that you cannot do with an operating system. An operating system would prevent you from doing direct I/O with peripherals, because the operating system would want to do that with its drivers, and the user code would just have to go through the drivers and would be operating at a much higher level of abstraction, which is the kind of code that you've written so far in our department. Okay, so the I/O registers are usually broken down into bit fields. Sometimes you'll have a whole register that's reserved for like one purpose, like like an address or something. But oftentimes you'll see different bit fields. And so here's one I made up where, you know, you've got you've got some flags and some bits and some, so they're named and they have bit ranges. And so the thing I covered last time was how to do bit twiddling, because when you write code that interacts with I/O registers, it's very common that you have to be able to both read and write specific bits and or ranges of bits, you know, inside these things. So you have to be comfortable with this style of programming. The nice thing about this is that up until this point, you might not have really had a chance to really use bitwise operators before. I mean, you certainly learned them in your, even in probably in 145, I would imagine, you know, you can do bitwise logical and shift and that kind of stuff. But you probably kind of wondered at the time. I know I did when I first learned. I'm like, well, when the heck would I ever use this stuff? I mean, this is supposed to be like, you know, doing arithmetic. Why are we doing bit manipulation? So this is an example of when you do a lot of bit manipulation. So for example, if you have a variable called val, and you want to set a specific bit to a specific value. In this case, I want to set bit 2 to 1. Again, the bits are numbered right to left from 0. So bit 2 is the third bit from the right. If I want to set it to 1, I'm assuming at this point it's currently set to 0. Now, if it's already set to 1 and I do this, what I'm about to do, that's fine. It won't make any difference because I'll essentially be ORing 1 with 1, which won't change the value. So it doesn't matter what current value that bit has. This is going to set it to 1. What I'm about to do here. So basically, I just have a temporary value that I initialized to 1. I shifted 2 bits to the left. Why 2 bits? Because I'm setting bit 2. And then I just do an OR, a bitwise OR. So this could be done in one line of code where you say val equals val or 1 less than 2. So this will do everything in basically one statement. Okay, so I don't even though I said there's a temporary variable called temp, obviously I'm just kind of inlining everything in one line at this point. But you could still have a temporary variable. This is just a kind of a coding style thing. Now, one of the things I mentioned last time was that this code has magic numbers in it. You know, you've got that 2. You know, someone reading the code might be thinking, why do you use 2? So that's not a great way to the code. So I'll show you better ways to do that here in a minute. This is just meant to show you the you know, the mechanics of it. Okay, so if I want to set bit 0, a specific bit to 0, unfortunately I can't do it exactly the same way. It's a little different operation. I still start out with a bit that I shift by a number of bits corresponding to the bit position that I'm interested in, which is 2. So I take the value 1, shift it to the left by 2. Now you might say, why are we shifting left? Because when the value of 1 is going to be a right justified value, which is going to be in bit 0. So the value 1 is going to be setting the least significant bit. So of course I have to shift left to get it, you know, to get it to the left. So I shift it by 2 bits, and then I negate it, bitwise negation with a tilde. I think it's tilde. Yeah, it's tilde, right? I always get this. Yeah, it's tilde. Tilde is a bitwise negation in C and in Java. And then you do an and instead of an or. So what this does is this basically ands the bit 2 with 0, which will 0 it out. And if it was already 0, that's fine. Makes no difference. The point of this, by the way, is that both of these things change the one bit without changing the other bits. And that's important when you're doing programmed I/O, because you oftentimes have to restrict whatever you're doing to specific bits. You don't want to wipe the whole register out. You don't want to have side effects and change bits that you don't intend to change. So this isn't me just being anal about this. This is critical. If you change bits that you don't mean to change, things will break. Okay, and then how about reading bits? If I want to read a specific bit, like if I want to read bit 3, well, there's different ways to read bits depending on what you want to do. In this case, I'm assuming we want to isolate it, so I'm going to shift it 3 bits to the right, and then I'm going to basically mask off. So I'm going to AND it with the value of 1, which will just retain the least significant bit, which is the original bit 3. And it's now in bit position 2 because I shifted it first. So again, the statement here is val shifted right by 3 and then ANDed with 1. And that should say, I'm being a little inconsistent here. Sorry. This should say val equals, right? Because I'm basically, you know, yeah. Well, that's assuming I'm rewriting val, but that's not a big deal, I guess. Okay, and then let's see. Another way to do this would be to not worry about shifting val, the original value, to the right, because that's only being done so I can right justify the isolated bit. If I don't care about doing that, like if I'm just using this for a, like an if statement, for instance, in C, then I don't need to shift it. I could just keep it in the bit position it is. So in this case, I just take val and I'm anding it with 1 shifted to the left by 3. So I'm running through this stuff fast just because this is a review. And then also, if I want to apply this to a range of bits, then I would shift right by the number of bits corresponding to the right number in the range. So generally when you represent ranges of bits, you put the larger number on the left and the smaller number on the right. So 5:3 means that the left bit is bit 5 and the right bit is bit 3. So in this case, we want to take bits 5 down to 3 in the original value, and we want to shift them 3 bits to the right, which will change the indices of those bits to, instead of 5 down to 3, it's going to make it 2 down to 1 in the new value after we shift it. So this basically positions those 3 bits on the right side of the register. Now in this case, we're probably, whenever you're handling a bit range, you're probably going to want to do this, because you're probably going to want to right justify it, because whenever you're dealing with a range of bits, you're probably going to be doing, some comparison or some arithmetic on it. So you're probably going to want these, you want to extract a multi-bit value out of a register, and you're probably going to want to make it, look like a normal value, right justified. So you shift 3 bits, and then you can AND it with a bit mask that'll knock out all the other bits that we don't care about. Now this part is a little confusing, so I added this slide that kind of summarizes these things a little bit. So the first 2 bullets there are how to set bit n to either 1 or 0, and this is being done in val. So I'm reading val as the input, and then I'm overwriting val with val. So I'm updating val with that 1, that bit either set to 1 or 0. And then in terms of getting a range of bits out, I have that 3rd bullet there. Okay, so this is a little bit more generalized. So this is where I'm saying I want the bit field that goes from bit n to bit m, and this is inclusive. This is inclusive. So this is bit n down to m, and of course n has to be greater than or equal to m, because n is the first number. It should be the greater number. It's the most significant of the 2 ends of the range of bits. So then you could take val and shift it by m to the right. So m is, again, the smaller number. And then to do the mask operation, you can subtract n minus m and then add 1, which will give you the total number of bits, and then use that as the shift amount for a 1 bit. Okay, so for example, in this case, like if I had 3 down to 5, this would be 3 total bits, because you have 5 down to 3 is 3 total bits, 5, 4, and 3. So what I'm doing is taking 1 and shifting it 3 bits to the right. That gives me an 8. So if I subtract 1 from 8, I get 7, which is 1, 1, 1. It's going to give me that bit mask with 3 1 bits. So by doing the shift to the left by the width, and then subtracting 1, it's a convenient way to get a bit mask that's right justified. So it's going to be 3 1 bits that are pushed to the right hand side. Now this might seem, by itself kind of simple, but I've actually been burned by this because of the operator precedence rules. If you look at hopefully you remember from 145, 146 about operator precedence. Sometimes the operator precedence is not what you expect it to be. So it turns out that in C, and I imagine this applies to Java and probably Python as well, add and subtract have, of the 3 operations that we're doing here. So we're doing add and subtract, we're doing shifts, and we're doing bitwise logical. It turns out that in C, add and subtract, of those 3, add and subtract have the highest precedence, and then shift, and then logical. Okay, so you have to be careful that you put parentheses whoops, I can't highlight that, can I? Yeah, when I do this 1 shifted to the left by n minus m plus 1, I have to be careful that I put that operation in parentheses because I want the shift to happen before the subtract. And no, I don't have to put parentheses around the n minus m plus 1 because the subtract and add there have higher precedence than the shift, so that will be okay. Although if you feel safer, of course, you can put more parentheses in than you need. In fact, it's probably best that you do that because, like I said, there have been many bugs in my code resulting from doing these bitwise operations and having the order of operations not go the way I expected. So I put parentheses here, and then so this should be correct unless I screwed this up. And notice also that the subtract here. So I take the shifted value, I subtract 1. That's going to happen before the bitmask operation because the subtract is higher precedence than the AND. So the subtract will happen first, and then the AND will happen next. If I had not put parentheses around this val shifted to the right by m, then that still would have been okay because the shift would have happened before the AND. So I didn't actually need the first set of parentheses there. So just be aware of that. And if you're unsure, you can either use parentheses or you just search Google for C operator precedence, and there's the first hit has a nice little list there. And then finally, the last bullet point is the other thing I mentioned, where if you just want to test a flag in C, if I just say if val and 1 shifted n bits to the left, that's fine. I don't need to. That's a simpler shorthand way to just test a flag because again in C, any non-zero value is true and 0 is false. So it doesn't matter that if I right justify the bit there for that isolation. Okay, and then I think this is the last thing I got to last time. How do you load and store in C or C++? You do a dereference to star operator. If you do it on the right-hand side, it's a load. On the left-hand side, it's a store. And I mentioned that now be careful here because you can get burned. I've also been burned by this. I did this once on a microblaze processor, and I didn't realize that you can't access I/O even on a bare metal system. You can't access I/O registers this way on microblaze because if you do, the cache will catch it, and there's no warning. You'll just get stale data. Boy, was that a hard bug to track down. So you have to read the documentation. Sometimes you have to use explicit intrinsics that map to special instructions. So sometimes a regular load and store instruction isn't good enough, even though that's fundamentally what you're doing with an I/O, programmed I/O. You're just doing load and store to special addresses, but you have to be sure that those loads and stores are not caught by a cache or any other thing that's assuming, or maybe the compiler does some optimizations that take those out. So you have to be careful with this. So I mentioned that like on some architectures, you have to actually use an I/O read, for instance, as I show at the bottom for reading, and an I/O write for writing. And those are intrinsics. Those are just like primitive. They look like functions or macros, but in fact they're intrinsics. They're things that are caught by the compiler and converted directly into assembly language. So yeah, just read the documentation. The reason I put this in, and this also relates to embedded systems, when we taught with the Arduino processor, the IO ATmega 328, which is the it's obviously not the only Arduino processor, but it's kind of the most common one. That architecture allowed you to just use loads and stores to do this, and that's exactly what we did. But you go to the FPGA-based processors that we use in 313, and you have to use the intrinsics, or if you don't, you can get in trouble there. Actually, to be more specific, well, there's no reason to get into too much detail there. Okay, so here's another. So going back to the example register, we've got some bit fields here. It's an 8-bit register. It's called it's labeled PNTLS. That's just the name from the data sheet. well, it's a made-up name, but it would be like a name that you might see in a data sheet for a register, because usually I/O registers are individually named. And in this case, I'm doing a little bit better programming practice, because I've got some pound defines. Hopefully you've seen pound defines in 240. So these are basically just constants that allow me to give symbolic names to magic numbers, essentially magic numbers being, you know, basically hard-coded values. So USB address is zero, yeah, is 0x100. So that's a hex value of 100, and that actually comes from that's the base address for the USB module. Okay, so the I/O space, remember, it started at 100 in hex, and then the PNTLS reg is actually an offset from that. So it's address 10 in hex or 16 in decimal that I have to add. You see that in the code under the first bullet. I add the USB address to the PNTLS, so that's kind of the base address for that peripheral. I add the offset, and then I assign it to a volatile pointer indicated by the star, and then I'm able to read the on fire flag by using the trick I showed you before. Now the difference is this time I'm not using that little that val variable. This time I am, instead of having a variable that I've read this value in, I'm getting the value of the control register directly through a dereference. So I say star PNTLAS, which reads it directly. Now in the assembly code, obviously you need like a whole instruction just to do that, just to read the value of the control register. But in C, I can inline these into a more complex statement. So I read the value of PNTLS, and then I in the assembly that would be in a register, and then I do my bitwise AND with 1 shifted by on fire. On fire is defined as 6. That is the offset within the register, the bit offset of the on fire flag. And then I shift it back to the right by on fire, so I can right justify the on fire. Now again, if I was just using the on fire in an if statement, I wouldn't have to do that final shift. And then there's a temp variable there where I shift by 3. Yes, that's the 3-bit temp field. And it doesn't stand for temporary, by the way. That stands for temperature. So I shifted by 3 to the right because 3 is the lower end of the range of bits, and then I AND it with 1 shifted by 3 minus 1, which will mask off all but the 3 bits of that field. So that will give me the value of the temperature field in the temperature variable. And then, so that's for reading. What about writing? Well, if I want to write the halt bit, I can dereference PNTLS on both the right and left side. So I can, on the right-hand side of that expression, I read the value, I read the old value. Now you might say, why do you have to read it if you're writing? Well, I'm reading it so I can make sure that I retain the value of the bits that were in there, aside from the bit I want to change, which is the halt bit, which is 7. So I dereference it, I load the old bit values, I shift in the halt, I shift 1 by halt to the left, which will position a 1 bit in the position of where halt is supposed to be, which is defined as 7, which is bit 7, and then I OR them together. And then likewise, if I want to set halt to 0, it's a similar process, except I have to negate the shifted value and then do an AND instead of an OR. So you can see it's kind of the sort of the opposite logically to set a 0. Let's see, wouldn't 1 shifted by the left by on fire, shifted right by on. Let's see, it's possible. Like I said, I always screw this operating precedent stuff up. So if I take, actually it would, oh yeah, you're right, actually. Yeah, that's a very good point, thank you. So let me fix that, that's a bug. So well, wait a second, yeah. So the problem is that the shift, as I mentioned, the shift will happen before the AND, right? So that's a very good point, thank you. I'm glad, that was actually turned out to be a good example. how you can get in trouble with this. So if I go up to that slide, right? So the shift happens before the bitwise logical, as I show here. So yeah, I want to shift it. I want to shift it first, then do the and then shift back. Otherwise, it would shift to the left by unfire, then immediately shift it right, and then it would and it with the PNTLS. So good, great. Well, that actually worked out pretty well. I'm glad that I had that bug in there, and I'm glad someone caught it. Okay, so that was Shrikar Ravi, by the way. Shashwat, thank you. Give you some credit for that. Okay. Okay, so this is a question from the exam last semester, or last spring, I should say, last time I taught the course. Write a line of C code that sets the value of bit 4 to the value of 0, or to the value of 0 in the variable named myvar, leaving the other bits unchanged. And the answer is, I take 1, shift it by 4 to the left, negate it, and then and with myvar, and that should that'll clear out bit 4. That's an easy one. This is a hard one. This upset a lot of students, this question. This one was, this question is about bit twiddling, but it's really more, it's kind of more of an exercise in kind of reading obfuscated code. But then again, I mean, you guys, you guys have some sympathy for us, because as instructors and TAs, we have to read a lot of obfuscated code. But anyway, the question is: consider the following snippet of C code. Indicate which of the following lines will cause the same value to be stored in the value y. So this is basically asking which of the 4 options are equivalent in terms of their behavior. I probably won't ever ask a question like this again, because this is kind of torturous. But basically, you kind of have to go in and try to decode it. So inside that line at the top, you're taking the value of x, shifting it to the right by 4 bits. Now, it's kind of hard to tell with the parentheses, but that value is shifted to the right, but it's never shifted back to the left. So what that's going to do is take now these are 8-bit values, keep in mind, because it's shown that they're declared as uint 8_t. So this is going to end up taking the upper 4 bits of x and putting it in the lower 4-bit positions, right, by doing well, that's the shift, right, the first shift. Okay, then, so you end up, so I'm trying to show that to the right there. So bits 3 down to 0 in the new value will be x, 7 down to 4. And then I'm going to do an OR, which is a merge, and that should work because, I shifted in 0. So anything I OR, it's going to, take on whatever I OR with. And then I take x, and I bit mask out the lower 4 bits, which is a hex value. F is 1111. So I take the lower 4 bits of x, okay, and then I negate it, and then I shift it to the right by 4, sorry, to the left by 4 bits. So that's going to take the original lower half of x, negate it, and put it in the upper half, and then OR those together. So you end up with is not x 3 down to 0, and then in the upper 4 bits, and then x 7 down to 4 in the lower 4 bits. So now you have to do that for the other 4 lines of code here, and it'd be kind of tedious, I guess, if I went through every step here. But the first statement does the same thing, except it negates the upper 4 bits, which before shift or after shifting them down to the lower 4-bit position. So you don't get quite the same value there. Option B ends up being the answer. It was equivalent. Option C ends up not. Does a double negate thing, where it negates the upper and lower half, shifts them the same way, but then it negates the final value again. So it does a double negate. So what you end up with is no negation relative to the original value. You just get, basically the upper and lower half of the bits swapped. And then option D ends up putting a 0 in the lower right hand, the right hand 4 bits are zeroed out. So the answer here is B. So yeah, this question is a little brutal because it's like I said, it's basically a test of how well you can interpret C code. Okay, so that's all we've got for bit manipulation. I'm going to switch topics here. This will be a very brief topic, actually. So pulse width modulation. I don't have much to say about this. We're covering it because it's very common in embedded systems. It's basically, so the problem here is that obviously CPUs are digital, but whenever they interact with the physical world, you have to do analog. You have to do analog conversion. So you need to go from digital to analog and analog to digital. The problem is that analog to digital converters are expensive circuits because they're big, but also they're sensitive analog electronics. And as a result, when you design the chip, you have to isolate analog circuits from digital circuits because the digital circuits are noisy. They cause noise from their shifting from 0 to 1 transitions and 1 to 0. They put noise on the power supply, they put noise in the substrate, and then they put crosstalk noise. So you have to be careful how you design analog circuits in a mixed signal chip. So ideally, we wouldn't have those. So how can we get analog? How can we do analog without any analog circuits? Well, you can kind of fake it with pulse width modulation. This is a way to implement an analog output value with the digital pin. So this would be in lieu of having a digital to analog converter, right? Which is, like I said, a specialized analog circuit. So the way this works is that you have a periodic signal, kind of like a clock, that spends part of the time 1, part of the time 0, and if you measure the amount of time from, say, like rising edge to rising edge, that would be the period that would repeat. So it's a periodic signal. It repeats over and over again. And the period, of course, you could measure that period in time, or you can measure, if you take the inverse, it's the frequency. But if you have the ability to change the duty cycle, which is the portion of that period where the clock is 1 versus when it's 0. And so when you take a signal like this, assuming that the period is short enough, and if you were to run this through a low pass filter, like if you basically have a way to take out the high frequency components that are a result of these sharp edges, these digital edges, right? The transients, the transient for going from 0 to 1 and 1 to 0 injects high frequency components. But if you have an ability to filter those out, or if you have essentially a DC system like an LED, for instance, that you want to vary its brightness, then if you take out all the high frequency stuff, this signal looks like an analog signal. The only restriction is that the analog value is going to be between 0 and the VDD, the power supply voltage for the digital signal. So, if a 1 is 5 volts, then you can represent a signal from, 0 to 5 volts. Most digital chips are much lower voltage than that now, but, some of the kind of the lower power ones, like the AT Mega, still use 3.3 or 5 volts. So basically, you have this signal, and it's periodic, and then so for example, if I have a 10% duty cycle, the clock is, or not the clock rather, but the PWM signal is high for 10% of the time and low for 90% of the time, and so this will start to look like basically 10% of whatever the VDD is. So if the VDD, the voltage, the digital voltage, the voltage when you're at 1, if that's 5 volts, then this will look like 10% of 5 volts, which is 500 millivolts, half a volt, right, 0.5. And this is how it will appear again if you're plugging this into an LED. So if you want to have an LED that can get brighter or dimmer, which is really common, you see that all the time now, like when you charge your laptop and the LED gets brighter and dimmer, so it's good thing for that. And actually, you can actually reproduce sound with this. In fact, this is actually how a Class D audio amplifier works this way, except it has a very nice low pass filter that they have to use to filter the output of the PWM signal. But even without that filter, you can do really basic audio, which is how I think some of the greeting cards work that you get in the store, you know, the greeting cards that play music. And again, LEDs. And then some motors work really well with this too. Like if you want to, you know, if you're connected to a motor, an electric motor. So this is a, you know, kind of a quick, now of course, also though, you can't put a huge load on this, obviously either, right? So, you know, with a motor, you know, you may need some, you know, like an amplifier or something there too, but because the digital pins aren't meant to drive a large load either. So there's a lot of restrictions here, but if those restrictions aren't a problem, that's pulse width modulation. So here's a question I asked on the exam last spring. Pretty simple. What analog voltage is generated with a 3.3 volt PWM signal having a 30% duty cycle? And the answer would be 0.99 volts. So it's basically just multiply. Okay, now switching topics again, let's talk about interrupts. So I mentioned programmed I/O was a process that can only be initiated by the CPU. So the CPU can initiate communication with any of its peripherals through programmed I/O by loading or storing, which is equivalent to reading or writing special register values on the peripherals. The problem is what happens if a peripheral needs to initiate communication with the CPU? It can't do that through programmed I/O. It's impossible. The only way for that to happen is for the peripheral to get the CPU's attention, and for the CPU then, once it has the attention, once the peripheral has its attention, then the CPU would then query the peripheral through programmed I/O, right? So this is a way to get the CPU to basically initiate an interrogation through programmed I/O, right? So this is a way the peripheral can get the CPU to interrogate it, to find out what's going on. So this is something that would happen whenever you have an event that is unexpected or unpredictable, like for example, if a packet is received on the network, or if a data transfer is completed, like the CPU initiates a data transfer between memory and the hard drive, and that transfer finishes, or even like simple as someone moving the mouse or hitting a key on the keyboard. Those are all things that require an interrupt, because the CPU would need to know when that happens. So basically, the peripheral initiates, the CPU responds, and there's also this idea, by the way, of exceptions, or sometimes called traps, that are very similar, basically the same thing. The only difference between an interrupt and an exception is that an exception is something that happens within a CPU, like a page fault, or a null pointer exception. Or sometimes an overflow, depending on whether overflows are trapped, or divide by zero error, or an invalid instruction, or any of the kind of things that happen inside a CPU. Those are called exceptions, but the principle is the same. There is an interrupt service routine, sometimes called an ISR, that is loaded in the operating system or the hardware abstraction layer, or in the user code, if this is bare metal. And when the interrupt occurs, then the CPU just automatically goes there and executes the code. And then when it's done, it returns back to whatever it was doing when the interrupt occurred. So this requires hardware support. Basically, the way it's physically implemented is that each peripheral has a wire that goes from the peripheral to the CPU. And sometimes the CPU has another wire, an acknowledge wire, that goes back to the peripheral. And we'll talk about the distinction there in a second. But basically, you need a dedicated wire. And of course, you can have more than one per peripheral, but generally each peripheral has one. So the peripheral triggers uses its wire to signal. When I say wire, I mean 1 bit. It uses that to signal the CPU, and then the CPU goes to its interrupt service routine. And typically, depending on the interrupt controller, usually the CPU will know which interrupt tripped. Sometimes it needs to check and figure that out, check a register. But usually there's an interrupt controller that goes between these wires and the CPU, and is sophisticated enough to have separate addresses to send the CPU for each interrupt, right? But that's not always the case. But the point though is that the interrupt happens, the CPU goes somewhere, and services it. The thing that we want to present here in terms of the material. Let's see, I get a question. Yeah, actually, so for a wireless peripheral, notice, and maybe, actually I should have made this more clear, I think. Let me back up here a minute. So that picture I showed of the chip. Yeah, so these peripheral, generally speaking, when I say peripheral, I'm talking about an interface, right? So a wireless peripheral would have to communicate back to the interface, the receiver on the chip, that it wants to do an interrupt. And then, but the physical interrupt itself would still happen in a wire between the wireless interface, the wireless radio, or well, I don't know if you'd make it, the radio / protocol stack, that would be all bundled together as the Bluetooth interface, right? That would be part of the system on chip. It would be one of these blue boxes, and the black wire here would basically, instead of an I/O pin, would be an antenna. But there would be a packet sent, a Bluetooth packet would come in. It would hit the interface, and then the interface would still just use a regular wire to interrupt the CPU. So yeah, that's how a wireless interface would work. But yeah, these interfaces could be Wi-Fi, USB, SATA, PCI, various types of memory interfaces. There's lots of interfaces. Like a cell phone chip will have, the LTE radio built in the Wi-Fi radio, and the Bluetooth radio built right on the chip. Because it's cheaper that way. You pull all the things right on the same chip. Now you might say, wait a second, Wi-Fi on a chip? I thought you said that analog and digital doesn't mix. No, they don't. But they have the fabrication technology of like a cell phone chip is very carefully designed to provide isolation and to achieve very good mixed signal performance. Back in the day when I used to design chips like that, this was back when I was in grad school, we used to use these, we had this fab called silicon on sapphire, where they actually, the substrate of the chip was made out of sapphire, which is a really good insulator, and then they would grow the semiconductor material on top of that, which allowed you to have perfect isolation between, there was no electrical connectivity whatsoever between the digital and the, except for the wires, of course, that you would run across the top of but there was no semiconductor, no active semiconductor active material that would allow the two sides to interfere. So yeah, so that's how that would work. Okay, let's see. Right. So I mentioned this, the way the interrupt wire works. Different processors use different ways to do interrupts. So one way to do interrupt is to have a simple wire that's level triggered, where when the interrupt wire, it's normally 0. When it goes high, the CPU is expected to go to its internet. Sorry, not internet. I keep saying that. Interrupt service routine, and then service the interrupt. This is actually one of the ways that you can do interrupts on the ATmega 328, the Arduino chip. The problem with this, though, is that this is very kind of dangerous, because there's no way for the peripheral to know if the CPU saw the interrupt or acknowledged it. Likewise, there's no way to know how long, the peripheral has no way to know how long it needs to hold that interrupt signal high. If it doesn't hold it high long enough, the CPU may not see it. It may, because sometimes you run things on the CPU that are not preemptible, not interruptible. Like, for example, if it's servicing a page fault, or it's disabled its interrupts for some reason, it's doing something important, it doesn't want to be interrupted. So there's no way to know from the peripheral's perspective how long it needs to hold that interrupt line high. So you run the risk, if you hold it high too long, you might actually accidentally trigger two interrupt service routines, because when the first one returns, it'll see that interrupt line still high, and then it'll go back and do another one. So you can accidentally do, this can be a concern. And as I mentioned, if you don't hold it high long enough, you may not get the interrupt at all. Another way to do it is rising edge triggered, which is where the CPU will only will actually somehow be able to detect the rising or falling edge of the interrupt line, which is a little better, but there's still no feedback to the peripheral, so the peripheral has no way to know if it was acknowledged. So here's a question I asked on the exam last spring. Suppose a peripheral is connected to the CPU's external interrupt input. Now, when I say external, keep in mind it's external to the CPU, but still on the same chip. We're all on the same chip. It's just external relative to the CPU, because the CPU is a module. Assume the peripheral can change the value of the external interrupt no more frequently than once every 50 microseconds. So when I say change, I mean, basically 0 to 1 or 1 to 0. Change the value. And assume the CPU can execute its interrupt service routine in 75 microseconds. What's the maximum number of interrupts per second possible when using the rising edge triggered interrupts or level sensitive interrupts? So for the edge triggered, you're looking for the fastest you can do it is, well, of course you're limited. So the CPU can run if it does nothing but run the interrupt service routine, it'll be once every 75 microseconds, because it can only do one, it can only service one interrupt at a time. But if it's edge triggered, you could, assuming that it's sensitive on the rising and falling edge, then you could ask the CPU to interrupt once every 50 microseconds. But obviously, if you did that, you'd be trying to interrupt faster than the CPU can service. So you have to take the minimum between the frequency of the frequency you get from 1 over 75 microseconds, the reciprocal of 75 microseconds, and the reciprocal of 50 microseconds, which is basically choosing between 13 kilohertz and 20 kilohertz. So 13 is the fastest that the CPU could be doing that. Now, by the way, this if you did this would be considered live lock, because the CPU would be stuck doing nothing but doing interrupt servicing. It wouldn't get to do anything else. So you'd kind of deny service to any other code that wanted to run. Now, the level sensitive, because you can only change the interrupt once every 50 microseconds, you would have to change it high, then change it low, change it high. That would have a period of 100 microseconds. Now, that's assuming that you don't just leave it high all the time, which you could argue that you could just keep it always high, but I'm assuming that we're toggling we're toggling the interrupt line. And so in this case, the bottleneck here would be the interrupt wire, which would be the 10 kilohertz, changing it once every 100 microseconds. Although, like I said, I mean, technically you could just keep it high, like I show in this picture at the top. Okay, now what about acknowledging? This is, so other heavier weight processors have an acknowledge line. This is what we have in 313 in the processor we use in that class. It's a little heavier weight processor, but there's an acknowledge line. So this way, the peripheral can issue an interrupt request, and then the CPU is allowed to take as long as it wants to service it, because it has this acknowledge mechanism. So it can say, it'll after some time has gone by, when the peripheral requests this interrupt, the CPU can decide to go to the handler, at which point it can have this acknowledgement signal come back to the peripheral, and then that will cause the peripheral to stop requesting the interrupt, because it has acknowledgement that the CPU saw the interrupt and is handling it, and at which point the CPU, at which point the peripheral will drop its interrupt request, and then the CPU will drop the acknowledgement. And the nice thing about this is that the CPU will refuse to service an interrupt a second interrupt until the peripheral drops its interrupt request. So in other words, this is a two-way handshake. This allows the CPU to notify the peripheral that it acknowledged the interrupt, and the peripheral can notify the CPU that it acknowledged by dropping its interrupt request. And so in other words, the peripheral in this case would always keep its interrupt high until the CPU acknowledges it. So this is a much nicer way to do interrupts. And so you could think of this, now I have these two little state machines down at the bottom of the slide here that indicate the very simple state sequence. So the CPU would be in a none state, meaning it's not doing anything. If it gets an interrupt, it would go to the handler state where it would jump to the handler, and then it would go to the acknowledged state where it would stay until it would, obviously in the acknowledged state, it would raise the acknowledged flag, and it would stay there until the peripheral acknowledges the acknowledgement by dropping its interrupt request. And then from the peripheral perspective, it would stay in the interrupt state until it sees the acknowledge. So there's just a little three-state sequence for the CPU and a two-state sequence for the peripheral. So it's nice and simple, and it ensures that there's synchronization between the CPU and peripheral. Okay, that's Philip's message. Okay, thank you, Philip. Yeah, so, okay. So here's some, I added this slide here, just kind of some steps to kind of explain this a little bit more clearly. So the steps is that the steps in performing an interrupt is the peripheral requests an interrupt, sets its interrupt output to 1. The CPU would eventually jump to the interrupt handler and then acknowledge the interrupt. I think the acknowledge, whether it acknowledges after it jumps or after it finishes the interrupt is up to the individual system. I actually don't know how Microblaze and the FPGA processors handle that, but I don't know when they do the acknowledgement exactly, but they acknowledge it when they decide to service the interrupt. And then the peripheral drops the interrupt request, and then the CPU will drop the acknowledge, and then the CPU is ready for another interrupt from that same peripheral. So that's another way to do interrupts. That's not the way the Arduino processor does them, because it's super simple, super lightweight. Okay, so now I'm going to switch over to this next set of slides so I can continue. Okay, so let's talk about, switch topics again, talk about interface channels and protocols. So communication channels, by which I mean the physical and the data link, meaning that you have different types of channels in terms of how bits are conveyed. Channels can be single-ended, meaning each bit is assigned to one wire, or they can be differential, where each bit is sent with 2 wires that alternate. That's for higher speed links, because that way any noise that affects one of the wires will affect them both, and so when you take the difference of the 2, it cancels out the noise. That's called common mode noise rejection. So you can run channels faster when you have 2 wires per bit. But also channels, as I mentioned, can be serial, which is where you just have the whole channel as 1 bit wide, or you can have parallel channels where you have like what you normally think of as a bus, which is a multi-bit signal that all the wires are routed together. Or you can have some hybrid approach like PCI, where you have different bit serial channels, but then you can have multiple channels that kind of build up a binded link, like when you have 16 channel PCI Express. You've got 16 bit serial links together that work that are bound. So there's different types of communication channels, but they're handled differently whether you're inside a chip, like within 10 millimeters, or if you're doing chip to chip, or if you're doing local area network type thing. So this all depends on the length. When I was in all the work I did in grad school was based on chip to chip channels. We did optoelectronic channels. We did packaging where we connected. We binded gallium arsenide chips, which allow you to do optical communication to CMOS chips using, you know, as I mentioned, the silicon on sapphire, and then we connected them to fiber image guides to try to build these packages. We also did multi-bit differential signal. Basically, it was all chip-to-chip links kind of stuff. Within a chip, generally you have buses. You have like multi-bit buses where, you know, and they can be quite wide. Like on FPGA, you can have 512-bit wide buses that you have to route together, which gives you a lot of bandwidth. But then once you go off chip, you generally are going to go to a serial interface. And then if you go to a local area network, you're either doing optical or you're doing, like, if you're doing Ethernet, it's like you've got this really high voltage, multi-level voltage scheme like Ethernet. You know, it's not, you know, it's not CMOS level voltages. You have to go relatively high voltage. So there's different ways to do these types of links. In chip to chip, you have different styles. Like you've got, for example, and different speeds, different performance. So you've got PCI Express and Thunderbolt, which are about 1 GB per second per channel. And then USB 3 and SATA, which are both about half a gigabyte per channel, 500 megabytes per channel. And then you have the low power links like SPI and I2C, which are designed not for performance, but for doing control, where you don't need a lot of throughput necessarily. But that being said, SPI and I2C have much lower latency than PCI Express or Thunderbolt. So if you need to get a message across the channel fast, your best bet is to use these low power SPI and I2C, because you don't have to go through all of the, you don't have to go through DMA, basically. You don't have to, you know, send the data through a memory and then have the peripheral go and access that memory. It takes time. There's a latency. So there's a trade-off here between throughput, you know, basically whether you want 500 megabits to a gigabit per channel, or low latency, which is where you then lose throughput. You're restricted to about 100 megabytes per second per channel, but you get faster latency. So SPI and I2C are ideal for doing control, where you're worried about latency. I need the message received from the time I send it. I need it to be received fast. I don't care how many bytes I can push through the channel necessarily, but the latency. And then there's UART, which is designed just for console I/O, just for a keyboard and a terminal, basically, a very low speed. So this is another kind of conceptual thing. Chip-to-chip channels, also called bus protocols, is, like I said, it's kind of the older term. They can be asynchronous or synchronous. Asynchronous is when you don't have a clock signal inside the channel, an explicit clock signal. You do clocking some other way, and you might say, why you need a clock? Well, you need to synchronize somehow. You need the receiver to know the rate at which bits are coming out of the sender, right? So you either put a clock in there, or you find some other way. And so if you find some other way, it's asynchronous, and with synchronous, you've got a clock. So UART, for instance, is an example of an asynchronous. There's no clock. And the way they get around that is they just have the sender and the receiver have to agree ahead of time what the bit rate of the channel is, and other parameters as well. But there has to be there has to be somebody, some human being has to be in the loop and ensure that the sender and receiver have consistent expectations of what the speed should be. Now, PCI Express and SATA are also asynchronous, believe it or not. As advanced as they are, there's no clock in there. And that's because they're so fast, it's not practical to put a clock. The way they work is you encode the channel. You use 10-bit, 8-bit encoding, where you take every 8 bits and turn it into 10 bits. Or they even have ones now on FPGAs that I use called 64 bits gets encoded into 66 bits. Now you might say, why in the world would you want to send more bits than you need to? You do that so you can maximize the number of transitions in the link. So that way, if you just happen to send a bunch of zeros, they don't come across as a bunch of zeros. They come across with a bunch of transitions in there because it's encoded. And that way, you can design an analog circuit called a phase lock loop that will recover the clock signal from the data signal. So basically the clock becomes embedded in the data signal. Now, it's not quite that easy. In fact, in practice, I've found that it's kind of a pain because it doesn't, in order for that to work, you not only have to encode the data in the channel, but you also have to put clock synchronization characters at regular intervals. Otherwise, you lose sync. So you have to put special control messages in there as well. So it's kind of a pain, although, the interfaces will take care of that, depending on what level of the abstraction you're working at. But we have an issue with a project I'm working on with the Navy where we have these chip-to-chip links, and we're using one of these technologies that use this encoding and embedded the clock and because these clock synchronization characters have to be randomly inserted, it ends up making the channel have a latency that's inconsistent. It's unpredictable, non-deterministic. Sometimes it'll be a longer latency, sometimes it'll be a shorter one, depending on whether it had to synchronize. So that's, anyway, I'm getting off topic. Synchronous is when you have a clock inside the channel. Okay, so here's UART. UART's very simple. There's 3 wires involved between the 2 endpoints. There's a transmit, a receive, and a ground. The transmit and the receive are crossed, though, between the sender and the receiver. So this one end will have its transmit going to the receive at the other end, and vice versa. And then there's a common ground that they have to have. Unfortunately, you can't get away from that. You have to have a you have to have a common ground if you're going to do electrical. You have to have a reference if you're going to do, unless you use, differential channels. But these are single-ended channels, just to be clear. So there's 1 bit per wire. So there's a ground. These wires are relative to this the ground. So as I mentioned with UART, they have to agree on a bit rate. This is a constant headache if you've ever had to plug a terminal into any kind of piece of gear, because you never know what the bit rate is. So it's always just basically a guessing game. Like if I connect my laptop into my a piece of equipment, laboratory equipment, you don't know what the bit, I mean, you could, if you look it up in the manual, but who does that? Generally, it's trial and error. You try all the different speeds until one of them works. So that's generally how UART works. So UART, when the channel is idle, the idle state of the channel is the voltage is VDD, is whatever the voltage is supposed to be to represent a 1. And then in order to send a word, and a word is generally 8 bits, but doesn't have to be. This is something else that needs to be agreed upon between the 2 sides. But before you send a word, you put out a start bit, which just means that the driving side, the transmitting side, pulls the voltage down to ground for 1 bit time. So whatever the bit rate is of the channel, I should say the baud rate, it's the reciprocal of that is going to give you time. So if it's a 9600 baud, then it's divide 1 divided by 9600 seconds. That's how long you pull it down. That indicates that you're starting. And then you send the bits serially. Now, what order do you send them in? Well, that also depends on the implementation. That's something else the sender and receiver have to agree on. So you might send them from most significant to least significant, or you might send them from least significant to most significant. But you send a series of bits across the channel, 1 bit at a time. And then you hope the receiver can reconstruct those bits into a word with the proper bit ordering. And then when you're done, you may have a stop bit, which is when you hold the channel high for one bit time. Okay, and that's really all there is to it. It's pretty simple. There's also an option for a parity bit, which would come after the data bits and before the stop bit. Now, again, if there is going to be a parity bit used, the transmitter and the receiver have to agree on that. They have to, agree that there is a parity bit. Now, keep in mind that with UART and with all these, I think all the interfaces we're going to talk about, the assumption is that the bits are transmitted consecutively in each bit time. So there's no way to stall the channel. You know, there's no way for the receiver to send 2 bits and then decide it wants to wait a little while before it sends the rest. Once you commit to a transaction, you have to go through the whole thing. You have to send exactly the number of bits that are expected in consecutive well, it's clock cycles, basically, if a clock cycle is the amount of time allocated for each bit in the channel, right? So these are all consecutive. You know, there's no like I said, you can't like stop and start. Okay, so parity bit. So a parity bit is an error detection bit. Allows you to detect errors if there was an error in the channel. And it's added after the data bits, before the stop bit. And then you can have odd parity or even parity. And this is something that I always have to look this up to make sure I'm understanding this correctly. But odd parity means that you want the bits that made up the data and the bit that makes up the parity bit together. So if there's 8 data bits and 1 parity, we're looking at 9 bits. And of those 9 bits, if you have odd parity, there should be an odd number of 1 bits. So what that means is when you're sending the data, if the data had an even number of bits, then you have to set the parity bit to 1. To make it odd, you have to force it to be odd using the parity bit. Now you might say, wait a second, I thought odd parity was if there's an odd number of bits in the data, then you set odd parity to 1. No, it's the opposite. If it's odd parity and there's an even number of bits, you set the odd parity bit to 1, because that way, if you look at all the bits that make up the transaction, there will have been an odd number of bits set to 1. And then likewise, even works the same way. If I have even parity, then I would set the parity bit to 1 if there was an odd number of bits, because that would force the total bits. The total transaction will have then had an even number of 1 bits. So that's the way parity works. And then baud wait, as I mentioned, was the rate in bits per second at which the data is transferred in the channel. Now that's not the throughput. The throughput of the channel would be the baud rate minus the overhead time you need to send the bits that don't convey any data, which would be the start, stop, and parity bits, right? So there's a difference there between the distinction between baud rate and data rate is that the data rate is the baud rate minus the overhead, the extra the control bits that have to be sent, right? The time needed for the control bits. Okay, so we have an example here. We're just about out of time though, so I'll start with this next time. But the only thing I want to mention about this example is I'm really proud of these timing diagrams. And you might not be used to reading timing diagrams yet, and if you're not, don't worry, I'll go over how to read this. But one thing I want to mention here is that when you look at this, keep in mind that UART doesn't require the transmit and the receive channel to be operating in lockstep. They don't have to be synchronized. Like when you send a transmission on TX, you don't have to also have a transmission going on the RX side at the same time. In fact, most times you don't. Usually only one pin is active at a time. Technically, it's full duplex. I mean, you can send and receive simultaneously, but because this is used for console I/O, you're never going to do that. You're going to type something on the keyboard and hit enter and then get the response back, right? So generally speaking, this timing diagram is not meant to indicate that the receive and the transmit wires are always, synced up. The bits, the transactions are lined up. It's not the case. Now, that is the case with SPI, and I'll talk about that when I cover SPI. Okay, great. So that's, I think, all the time we have for today. We have a couple minutes left for questions. If anyone has a question, you can post it to the chat, or you can talk. I don't care. I don't know if you can talk. But if anyone has any questions, let me know. So, just to kind of give you give you kind of a preview. So we're going to cover first assignment. I don't know when the first programming assignment will be. We're still working that out, but the first quiz will be next week. I'll assign it. We have Monday off, so I was planning on assigning it like Tuesday and then giving you to the following Tuesday to do it. But no, we won't have a we won't have an assignment for until at the earliest it will be the week after next. Yes, the quiz will be multiple choice. The exams most likely will be multiple choice, although I would like to move away from multiple choice if possible. So other professors have done a thing, and I'm sure you guys know more about this than I do, I'm sure, because you've had, you know, by this point, many different classes that have been done online. But some professors have you just like write it out and take a picture and send a scan of the exam, so you could do it on paper. We could also do, you know, fill in the blank questions on Moodle in short answer, and they just have to be graded. And it's the reason we don't do that is not because we don't want to grade them, but it's because generally in a class like this, you know, when I would give a regular exam, you know, I'd have you draw a block diagram or write out some equation or something, and that's hard to do even if you can, you know, have a text field on Moodle. So, but right now we're going to do multiple choice. I just don't think that's a great way to do tests, but that's the plan for now. we might adjust that. Okay. Any other questions? Okay. Well, good. That sounds good. I think this went pretty well. I'll post the recording as soon as I can on Moodle. You can access the recordings on Dropbox too, I believe, but it's really hard to find them. It took me a while to track it down. But I'll just post a link on Moodle. I think that's the easiest way to do it. And if you have any questions in the meantime, feel free to send an email. I won't see you on Monday because of the holiday, but we'll be back on Wednesday, next Wednesday, a week from today. So I'll see you guys then. Thank you.